In this video, I will present you Epsilon Aero Data. This is basically a filter that computes all the aerodynamic analysis methods, starting from your CFD or wind tunnel data. Basically, you have to load first your input data into ParaView. This could be either CFD or wind tunnel data, and then you should have to apply the Epsilon Aero Data filter. These filters will allow you to perform several operations. First of all, it will provide you some aerodynamic parameters. What you're seeing here, for example, the pressure coefficient at the surface. You can also compute, let's say, the Q criterion to identify the vortices. You have some shock detection parameters that allow you to visualize the shock wave, and some weight parameters to visualize, let's say, the energy, the profile drag, and so on. So basically, it will provide you some aerodynamic parameters, a lot of aerodynamic parameters that are useful for understanding the physics. But the basic idea, the main objective of Epsilon Aero Data is to provide some specific aerodynamic analysis parameters. You have the wake-reduced versions of some far-field and exergy formulations that basically will provide you, let's say, the drag density at each point of the wake. But you also have the standard full plane formulations for either exergy and far field that will give you the local drag density at each point of the survey plane. So in order to achieve that, I will show you how it works internally on the background, what is done on the background inside ParaView, how it processes data, and how it starts from the original CFD or wind tunnel data in order to obtain this desired result. Well, in order to see that, we have to understand first what's the kind of data we are using. I will show you the example of the CFD data. Basically, it can be of different type. It can be either 2D, 3D, or axisymmetric. The grid type is different. It can be structured, unstructured, and so on. You are familiarized with that if you are doing CFD already. We have to deal also with grid partitions. It can be single block or multi-block. The case of multi-block is typical of multi-process computation, or even if you do grid adaptation, the part of the grid that has been adapted in order to refine the wake or refine the shock wave position. It will be loaded inside ParaView as an extra block. So in those cases, I will have multiple blocks to deal with. And also another particularity of CFD data is that the amount of available parameters will change depending on the type of solution you run. In a standard way, you know that static pressure and velocity will be always available, but density and temperature may not, depending on the way you set up your CFD solution. So all these variabilities must be taken into account in order to process the data in a uniform fashion, regardless the CFD solver, the CFD setup, the type of mesh, and so on. So let's see how we can manage all that. The first step to deal with that is a pre-treatment procedure. Basically, the first step is to extract blocks. As I mentioned before, we have, in the case of grid adaptation, for example, we have at least two blocks. One gray block that's the background domain, the entire domain basically. And ParaView, when loads adapted grid, creates an extra block on the refined region. This extra block is undesired and is overlapped on the top of the grid domain. That's the actual domain. So I had to take away the red part, take that to the trash, and retain only the grid block, the block 0, that contains all the physics information. So that's why we included a BTK operation that performs this block extraction. Then I have to perform merge blocks, because even if you don't have this type of mesh, if you have just a single block, when you load that file into ParaView, sometimes you have multiple blocks, especially when you have multiple IDs for different surfaces, for the body, for the far field domain, and so on. You have multiple blocks for that, and you have to merge all this information together, and that's why you have to use merge blocks. This is also useful if you have performed a CFD simulation in the server where you have multiprocessor domain split like this, as you can see here. And afterward, we perform a cell data to point data operation because basically ParaView is a point-based approach. If you are using cell-based simulation, this information will be converted to point data information. This will have some impacts in accuracy. We'll see later on. It's quite safe for us to assume or consider point-based data, but in some specific cases where accuracy will be compromised, we'll see that in Epsilon Nearfield, for example, we retain the cell data, or if your input CFD data is already in the point-based, it will convert it to cell-based solution. As you can see, all of these are BTK operations that are on the background. You don't actually see it, but it is included inside the Epsilon Aero Data Python filter. Just to take a look at that, if you open the epsilon aerodata.py file inside the Epsilon installation folder, you can identify this operation as a BTK merge blocks, and you can edit the option if you want it. All the code is available to further manipulations. Now that you have a condition of the initial CFD data, you are ready to standardize all the parameters that will be used afterwards to compute all the aerodynamic analysis method. And that's why we decided to implement readers. Why? Because we have to deal with a lot of CFD solvers. Particularly for this tutorial series, I will use Fluent CFD solutions, but you can use either Star CCM, ELSA, IceCube, or whatever you want. So in order to deal with all these different CFD solutions and the different parameters that this solution can provide, we're using specific readers. First of all, we have to deal with the type of parameter we have disposed at the input file. And we also have to deal with the different head name associated to each different CFD solution solver. So that's why we introduced the reader. Basically, it loads existing arrays that are available on the input data, and it returns a specific set of Python variables. So basically, if you open the Epsilon Aero Data Python file, you will find a lot of lines like this, where you have basically a reader class that it reads the input data, that is your CFD data that you just loaded into ParaView, and it delivers just a series of Python variables that contains the coordinates, the static pressure, temperature, and so on. Even if your CFD file, for example, doesn't have static temperature, it's not a problem. It will just give an empty static pressure variable, and then the code will automatically recognize that the temperature is not available at the input, and then will allow you to complete the missing field. So there's no problem. Everything is managed by the reader, specific reader for each particular solver. In my case, I will use all the Fluent reader, but if you are using other CFD solver, you will have to use a specific reader, and that's accessible on the interface. We will talk about that later on. Now that we have all these parameters, let's say pressure, temperature, and so on, these are Python variables, I can actually compute the remaining flow field parameters. Basically, let's say one of the parameters is missing. For example, if you didn't activate the energy equation in Fluent, you will not have the static temperature. And in that case, you can complete the missing field, the missing parameter, by either assuming isoenergetic, isentropic flow. You have some options to deal with. Because, for example, if you actually activated the energy equation, you will have the static temperature, and in that case, you want to use the input value. You don't want to recompute that. So you have several options depending on your needs. Afterwards, you have to establish the upstream reference values. Indeed, far-field and exergy methods require specifying the upstream reference values in order to compute the changes of velocity, changes of entropy, and so on. So you have to specify that in advance. And you can do that in two ways. You can enter these upstream reference values by hand, or you can let the code to extract these values automatically from the CFD data. And this is the option that is activated by default, and we will talk about that later during the practice session. Basically, what it does on the background inside ParaView is to perform a series of BTK operations. The first operation is to identify the surface of the entire domain, the external surface of the domain, which includes, of course, the boundary conditions. So what we do is to generate a survey line that starts from the body and goes up to the survey plane with a specific angle. That's the angle of attack that you declare on Epsilon Aero Data. And this allows us to define a point, an intersection point between this line and the boundary condition domain. And this green point will give us the information of the, let's say, velocity, pressure, and so on at that point. And basically, this will give us the upstream reference values. Of course, you can use this if your domain size is large enough. If your domain size is very small, or you don't know, you are not using CFD, sorry, in that case, you have to enter the upstream reference values by hand. Now that you have declared the upstream reference value, you have to transform the reference system. What is this? Indeed, the standard conventional aerodynamic axes are usually different from the mesh axis. All the aerodynamic analysis method use this kind of axis as default, with the x-axis pointing downstream, y-axis pointing to the right-hand side of the body, and the z-axis pointing upwards. Your mesh axis instead might not follow this convention. You might have, let's say, the y-axis pointing upwards. That's one of the cases. But the most classical inconvenience that we have is that the mesh axes are usually linked to the body. So when you change the angle of attack in your CFD solution, the mesh axis will no longer be aligned with the aerodynamic axis. So I had to transform all the vector quantities from this reference system to this reference system. Afterwards, once I have transformed all the vector parameters to the aerodynamic reference system, now I can tackle the computation of the aerodynamic analysis methods. And here I compute the classical aerodynamic parameters like total pressure deficit, entropy generation, and so on. But I can also compute other parameters that are related to the aerodynamic analysis methods like far field, land vector, and exergy. Please note that the near field method is not computed inside Epsilon Aero Data. Instead, it is computed in a separated filter called Epsilon Near Field, and we will see that in a separated video. Epsilon Aero Data also allows you to define what I call the UDV, the user-defined variables. So let's say you want to introduce your own equations, you are developing a new drag prediction method and you want to implement some parameters that are not pre-foreseen in advance in ParaView, in our code. You can add new arrays, you can generate new scalar quantities, new vector quantities, or new tensor quantities, and implement your own new analysis method. So this is quite powerful, and this was a feature that was demanded by our users, and it seems to be quite practical. Once you compute all these variables, you should have to output this data in order to display that on the screen, and this is performed by using BTK operation. And what you get, the output of Epsilon Aero Data, is a BTK unstructured grid type. If you want to understand the BTK operation and the BTK types, please take a look to our BTK and ParaView formation video in a separate link down below. The output of this filter, the Epsilon Aero Data, will contain two kinds of attributes, point data and field data. Point data is basically what you see on the screen, that for example the velocity and pressure at each point of the domain, but you will also have some field data. Field data, for example, will keep inside the output file some information like, let's say, for example, the angle of attack, the upstream reference values. These are just single values that are stored in the file, so you can use that afterwards to remind what you have done and also to transmit this information to the other filters that are applied on the top of Epsilon Aero Data. So as I said before, point data contains all the aerodynamic parameters that you compute, and the field data will contain some reference values and some specific information. The interface, basically all what we discussed before, is included on the GUI of Epsilon Aero Data. As you can see, many of the parameters that we discussed are here. You can control that, and we will discuss that in detail in the following live demonstration. The practical part of the tutorial, we will use the open data available in our website. So go to our Epsilon website, click on Open Data, CFD Data, and we will use this case. The 2D subsonic case is a NACA 12 airfoil corresponding to an angle of attack of 10 degrees on Mach 03. So just click here and you will download the file. Just click here and start downloading it. Now I will open the file. Now that I have the CFD data open, I can apply the Epsilon filter. So here you have all the icons of all the filters, and all these are sources. For CFD data, you will only use these icons. These icons here are for wind tunnel data. So in our case, we'll use in particular this one, that's called Epsilon Aero Data. Click here and will appear here. And now you have to set up all the parameters of the filter. Just before clicking Epsilon Aero Data, make sure that this option, Auto Apply, is not activated. If that's the case, each time you modify some parameter here, it will execute the filter, and that's quite a lengthy process. So the most safe approach is to be sure that it's in gray, it's not dark gray. Basically, it will allow you to set up properly, and then when you click on apply, it will execute the Python code. So having said that, let's start with each one of the elements inside the GUI. First of all, you have type of data. Currently, you have steady or unsteady. Epsilon V3 only deals with steady data. We let here unsteady because we are developing the Epsilon V4 version currently. He's using this unsteady option. In your case, just let that steady. Afterwards, you have to select the data format. In my case, a Fluent case, I let that by default, but you can select any other existing solver, or you can even select a new format that is not actually covered. I will explain you separately how to generate a new format and how to define any of these options as default option. For the moment, we stick here to the Fluent cast file. Afterwards, I have to define the upward direction. I mean, this is the mesh. Let's put always here 2D to 3D. This will facilitate the way you manipulate the object. I just go back to this CFD data. When it's blue, it's activated by default. And I will show, for example, the static pressure of this. And basically, as you can see, this is the 2D domain, and the mesh upward axis is the y-axis. So in Epsilon Aero Data, in upward direction, I have to declare either y-axis or z-axis. In my case, it's y-axis. Afterward, I have two options One is reconstruct the static pressure, static temperature, and density fields, and the other is adaptive mesh refinement. If you are using CFD data with the energy equation activated, you will have pressure, you will have density, and you have temperature, so you don't have to worry about that. That's my case. In fact, my input fluent data, I have pressure, I have temperature, and I have the density. All this varies on the entire field. There's no constant density, no constant temperature or something like this. It has been well solved, this Fidelic solution. If not, let's say this is not your case, you have performed, let's say, incompressible solution without the energy equation. In that case, you will not have temperature, for example, or your density will be constant. This will not provide accurate solutions because this is not the real physics. It's just an approximation. Epsilon allows you to overcome this problem, and you can select the reconstruct PS-TS row fields. By default, as you can see, static pressure, temperature, and density use the input arrays. In my case, since these fields have been properly computed in the CFD solver, I can let it as default or even deselected. That's okay, it will compute the correct aerodynamic analysis parameters. But if not the case, let's say, for example, you have computed your CFD solution with constant density, you have to improve that because in reality density is not constant. It changes a little bit, but it's not constant everywhere. And in that case, you have to introduce some assumptions. In your case, you can assume either isentropic, isenergetic, ideal gas. I'll let you play with that depending on your needs. But in my case, I will let just the input values. In fact, I can deselect that as a default. The other option that you have is adaptive mesh refinement. It is not my case. In my case, I have some details. Let's click here. In blue is the element active. Go to information, and it will show you what you have. My input data, in my case, is a multi-block. If you scroll down, you will see the input parameters. In particular, you have to pay attention to this. It's a multi-block, but I don't have a grid adaptation. So basically, I don't need to click here. If you have a grid adaptation, you have to click here, and then you have to specify the ID of the block that you want to extract. As I show you in the presentation, you will find a gray background block. You can actually color this by ID blocks ID, exactly. These are the blocks and all the IDs. As you can see, I have a single block, everything is gray, that corresponds to the block 0. If you have some grid adaptation, you will have some other colors corresponding to the other blocks. Well, all these blocks has been taken away, so you have to retain just the block 0 that corresponds to the background entire flow field. So if that's your case, if you perform a grid adaptation of the wake or the shock wave, you have to extract the block 0 because 0 corresponds to the background block. It is not my case, so I will not activate that. Afterwards, I have to indicate the upstream reference values. In my case, it's 2D case with angle of attack 10, so I have to indicate that here. Since it is 2D, there's no side slip angle, so I let that in 0. And then by default, it gets the reference values from CFD data, the reference static temperature, static pressure, and upstream velocities. And this is made, as I showed you in the presentation before, automatically by using BTK operations. But let's say you want to specify that by hand. Well, you just click here, and you have some options to specify that by hand. In my case, Mach number is 03. So airspeed type, you have two options. You can either specify the velocity, either specify the Mach number. In my case, I will specify the Mach number, and it is 03. Sorry. And parameter type, it corresponds to the pressure and temperature. In my case, I know it is static temperature and pressure, so I will let that static. Otherwise, I have to select total values. So in my case, it is static, and I let these values as default. So for me, it is okay, and for the input data that I provide you in the open data, it is okay, but you can let it as it is, or simply, you can let that click by default. It will be automatically correct for any CFD data, as long as the upstream boundary conditions are far away from the object, and this is the case of the open data that I provide you. If not, you are forced to use this because extracting data from the reference point, the boundary condition will provide you some errors when the boundary conditions start getting closer to the body. So, upstream reference value, it's okay. Now we can go to non-dimensionalization. By default, all the output values will be non-dimensionalized. That means if you compute drag, it will give you the drag coefficient by default. If you don't want to compute drag coefficient, you actually want to compute total drag in newtons, you just have to click here and that's all. Another thing, if you non-dimensionalize, you have to specify the reference surface. In my case, in your open data, you have the reference surface here. It's an airfoil of core 0.435, so that's the value that I let by default inside the Epsilon Aero Data. Afterwards, you have to specify the output variables you want to compute. By default, everything is compute. You compute the aerodynamic parameters and all the aerodynamic analysis method. But this is quite memory consuming. It will increase your memory size. Let's take a look at that. You can see this is the actual memory that I'm using. If I execute Epsilon Aero Data, it will take some few seconds to compute everything. Just remind that the amount of time that will take to compute the entire solution depends on the amount of parameters. When I say amount of parameters is, you just click here, make sure this is blue, and it will show you all the parameters that it has computed. You can see there are a lot of variables that are computed on the background. For example, it computes the static pressure coefficient. I can take a look at that. And each variable increases the amount of memory consumption. We have started here, now we are here. But in this case, of course, it's a 2D case, it's not memory constrained. But if you have a 3D case with a lot of millions of cells, you will hardly reach the limit of your memory of your computer. So you have to take care of that. If that's your case, you have some constraints in memory, you can just compute what you specifically need. Let's say I just need the pressure coefficient. I don't want to compute any of the far field method, exergy method, and so on. So if that's the case, I just go to analysis method and select none. So it will not compute the analysis method. It will just compute the aerodynamic parameters. And when you apply, you will see that all the amount of variables that I had before has been reduced. This time I just have the aerodynamic parameters that are marked as aero. And that's all. These outputs, that means what you can see on the screen, that each point of the mesh is marked as a point here. The point means that this parameter is a point data, and this is something you can visualize on the entire field. For example, let's take a look at the total pressure deficit. Total pressure deficit is on the entire domain. But also you have some parameters that are marked with this red circle, this yellow circle here, and this is extra information. The best way to visualize this is by clicking here to create a new layout, and click on Spreadsheet View, and select first the element you want to visualize. Epsilon Aero Data is my case, and in Attribute I want to visualize the field data. That's what I want to visualize. And each one of the parameters that you can see here is extra information, just a single value. For example, the angle of attack that I defined in the GUI, it's there, because this information will be transmitted downstream to the other filters that are applied on the top of Epsilon Aero Data. And also you have other specific information. For example, when you get the upstream reference values here automatically, when you click on this option, you don't know what are the values. So you have two things. These values are printed here. It computes, it identifies the values here and prints the information. But also you have the same information here in the field data. You have, for example, the upstream Mach number is almost Mach 0.3. Now let's say you want to compute some specific aerodynamic analysis method. I don't want to compute the aerodynamic parameter, so I deselect that. And analysis method, I will select, for example, exergy method. I will select ARNS method, that's the initial exergy method. And when you apply, it will only compute the ARNS method. And as you can see, this time we have only the ARNS formulation. For example, if I plot the drag coefficient, I will have the entire density of drag coefficient at each point of the domain. And the physical analysis of this will be studied in a separated video. Now we're just trying to help you to understand how to manipulate the interface. Of course, you can select any other method. For example, far field, if you want to also select specific far field method, like let's say bets, that's a weight reduced method. It will also, besides ARMS, it will compute bets. You can select or deselect whatever you want. And this time when you execute Epsilon Aero Data, you have ARMS, but you will also have bets. And again, you have the profile drag density at each point of the domain. This allows you to select the standard variables, but let's say you want to specify your own variables. You can use that by clicking here, user-defined variables. When you apply, you will have also here as UDV, the scalar and the vectors that you created in the Python file. And I will show you later on a separated video how to create new parameters, what you have to modify in the code to add that. By default, I have two example cases that a scalar and a vector arrays. And this information is just qualitative, it's not an actual parameter, but I let that just to show you how it behaves. But again, we'll see that in detail in another video. And at the end, this is not mandatory, but you may you have access to some advanced options. Just make sure that you have clicked here on the small gear. This gear basically is a button that allows you to visualize the advanced options of any interface of ParaView. This is not just an Epsilon feature. This applies to any interface in ParaView. So in this case, if you click on the gear, you will have access to the advanced option where you have some specific tools. For example, let's say your CFD data was made in millimeters. Well, you have to convert that to meters because Epsilon works with SI International Standard Unities, which means that the geometry must be generated in meters. So you have to scale geometry, if that's the case, and you have here the scale factor. In my case, the open data that I provide you is actually in meters, so I don't have to touch that. Then you have another option called define gas constants. Basically, what you have here are the constant values used on your CFD solver concerning the gas constant R, gamma, the turbulent prand. These values that are here correspond to fluent solver. Let's say you perform your CFD simulation with another solver. Well, these values will change very slightly. In order to improve the accuracy of your analysis inside Epsilon, I strongly recommend to update these values depending on the value that is used in your actual solver. It is not my case, so I will not select that. You can also save your output in BTU format. When I say output, I mean the geometry, the mesh, what you see here, and the data. When I say data, I say the point data that I have computed and along with the field data. All this information will be stored in a BTU format. And if that's the case, if you want to save what you're seeing here in a BTU format, just click here and specify the output path And that's all. Once you apply, it will save that in a BTU format. Just keep in mind that this BTU format is a standalone file, so you can share that file with your colleagues and they will be able to open that file without the need of studying Epsilon. It's just a standalone file with all the information that you just computed inside Paraview. And then the last option is called Select Array to Pass. If you click that, you will have access to all the input parameters. To understand that, I will go back to my CFD data here. Remember, if I click that and it is blue, it's the active element. And this will allow me to visualize all the parameters that are related to this file. Well, in this case, I have all the cell data of the input CFD data. You can realize it is cell data because you have here a yellow cell, otherwise it will be a yellow point. The standard Fluent file will give you cell data, so that's what you get at the input. For example, there are some parameters that are not taken into account by Epsilon. For example, wall distance, that's the distance to the object, is not read by Epsilon Aero Data. It's completely ignored, this parameter. And let's say inside Fluent or inside your CFD solver, you can compute extra parameters, and maybe you want to use these parameters for your aerodynamic analysis. So let's say in this case it is wall distance I want to use in my analysis. Well, unfortunately, Epsilon will not take into account wall distance by default. However, there is a way to overcome this. So in your case, let's say you want to send this parameter wall distance to the output. Just go to Epsilon Aero Data, select Arrays to Pass, and check this parameter, wall distance. When you apply, it will be at the output. You can see here wall distance along with our parameters, the UDB, BES, or ARMS method. And that's all. These are all the parameters you can modify inside Epsilon Aero Data. Keep in mind that this is just a presentation of the entire interface. We will see in detail how to use Epsilon Aero Data for an actual aerodynamic analysis in a separated video.